So welcome everybody. Again, we want to say thank you for attending the fifth webinar that Bad Elf has been putting on for the last few months. I see some familiar faces and names in the attendee list. So for everybody that's been attending these, we want to say thank you for coming back. Hopefully you've been enjoying and more importantly, learning some things during these webinars. Also, for all the people out there that I am not familiar with, welcome. Good to see some new names on the list as well. So welcome to Bad Elf's fifth webinar. My name is Nicholas Smolofsky. I'll be your co-presenter today with Larry Fox. Larry Fox is the Vice President of Marketing and Business Development, but don't let that fool you. He's also an engineer at heart. He's going to be primarily talking to you today about how the Bad Elf Flex can operate and utilize now both the geoid transformations and orthometric heights. I just want to make a quick comment that if you're unfamiliar, Bad Elf, we've been around about a decade now creating cost-affordable GNSS receivers. We love talking with our customers, and we've decided to be running these webinars to have a outward-facing engagement with everybody. So if you have any questions during this presentation, please feel free to put them in the chat. Larry and I will address them at the end. Please know as well that we will be recording. And so this will be recorded and posted on the internet through our social media platforms, probably within about a week. Also, if speaking of social media platforms, if you are not already following us, we would love for you to follow us on LinkedIn, Facebook, and Twitter. We are also posting all of these videos to YouTube. So without further ado, I would like to pass the digital mic back over to Larry Fox to get us kicked off here for this webinar. Again, if you have any questions, please put them in the chat. We will get to them at the end. And Larry, without further ado, it is all you, sir.
All right. Well, thank you, Nick, for the introduction. I really appreciate it. Hopefully everyone can hear me okay. Nick, you could hear me, I assume?
You are coming in loud and clear.
Good deal. So I'm very excited to talk to you about this latest feature that we have coming up for Bad Elf Flex. So here's a little agenda slide that we're going to go through. I'd like to chat a little bit about just a review over height measurement. We're going to talk about this new geoid feature enhancement. I'm going to go through a couple of slides on how it's going to look like in the Bad Elf Flex app and on the Flex itself. I'm going to do a little bit of a dive into what some of the recorded data is going to now look like. And then Nick is going to talk about how this all works into a GIS type of application. So how you would use this data and bring it into a GIS. Of course, we are going to be giving away a hat at the end, and QA will follow. So we'll try and stay on for as long as we're getting questions and help support talking about this new feature. So we're planning on running this for about 30 minutes, and I think we're going to be in good shape for that. 25 minutes will be allocated to the presentation, and then 5 for Q&A. But like we said, if we're still getting questions, we'll continue chatting with you guys probably for up to a half an hour. So if I can get started. Let's talk about the basics of measuring height a little bit. Measuring height is a really interesting thing with GPS receivers, and I thought I would bring a pretty picture in to get y'all started. This is actually a view of a point cloud of data that we flew with a drone a while back, and what you're seeing actually is a point cloud maps to ellipsoidal data, which is what's generally produced by a GPS receiver, and how that shifted with the real world. And so one of the things that's really, really critical for many uses in the GPS world, or for those who are collecting data in this environment, is being able to map things to real world heights. So one of the things that we did at Bad Elf is we explored how others are doing it and what the science involved with all this is, and it really comes down to making sure we have good geoid models to map all this GPS data to real-world orthometric heights. I'm not going to go into a deep dive on the science behind geoid models, but I do want to go more into the feature. If there's some discussion you'd like to have on the science side of it, we could definitely take that offline, but for today, you've probably, or some may or may not have seen this formula where orthometric height is equal to the ellipsoidal height minus the geoid separation. So that's about as intense as we're going to get into math today. If you look at that picture and you imagine that I take this GPS data that's at an ellipsoidal height and add the geoid, that would have brought it back up to the Earth. And that's really what we're after today, is how could we, producing a Bad Elf Flex with internal geoid models, help you to just have data that actually matches to real world coordinates. I did want to bring up that pole heights and antenna reference points do affect this, but we're going to show a really nice picture of what that means coming shortly. So moving on from here, Bad Elf, we do like our pictures, and we'd like to include a little bit of elfage in all of it. You might have seen this picture before, probably not as pretty. We'd like to think that this picture is really descriptive, but for all intents and purposes, we wanted to exaggerate what's really going on in the real world. GPS receivers produce heights based upon an ellipsoid. If you could imagine, your ellipsoid is just a representation of the sphere of the Earth being not perfect, but what GPS thinks is a standard kind of sphere. Really works well for the most part. GPS receivers also apply their own geoid to things, which gets you really, really close to orthometric height, but it's not quite exact. So when we add a geoid to an ellipsoid value, assuming our geoids are highly accurate, we actually get a very good representation of what your location is truly on the Earth's surface. If we look at that picture over there on the right, you'll see me flying a drone and one of our receivers on a pole. So one thing we want to highlight is the height that you place the GPS receiver does have an effect. So we publish that our antenna reference point is 23 centimeters above the base of a Bad Elf Flex unit. And I have this on a 2-meter pole. So we're offsetting our final measurements by 2.23 meters. So just some things to keep in mind as we're trying to get as accurate of height as possible. If you want your data to really match up to real world conditions, all of this really does matter. So moving on to the next slide. What we've done with the Bad Elf Flex is quite interesting. So we've added full orthometric height support directly on the Flex through the Bad Elf Flex app and in all the data that's logged by the Bad Elf Flex. Not only have we added orthometric height support, but we've added both forms of geoid, whether you're operating autonomous, which would be kind of in an SBAS mode, or without SBAS, or through a corrected mechanism such as RTK. We have datums available. This is the list that we're starting with, and it covers the US and Canada. So a couple of special things I did want to mention on this slide. Geoid 18, for example, in North America is the most accurate one that we have available, but it currently only covers CONUS, the continental United States, and Puerto Rico. So for those of us in Alaska and a few of the other places, you'll have to back off onto Geoid 12B. A couple of notes with regard to Canadian data. We do actually support both forms, ITRF08 and NAD83, and the Canadian geoid will map to the Canadian Spatial Reference System. What we've done in the BAD-L Flex as well is allowed for auto switching. So for example, when you're in SBAS mode, you'll be using the USG 2012 ITRF08 if you're in the US or the Canadian system while you're in SBAS. And the moment we detect that RTK fix occurring, we'll actually automatically switch to the appropriate geoid. I'm going to show you a little bit more about that in a couple of slides. Whoops. Getting a little clicky here. All right, so what does this look like to configure? So when one configures this, they would go into the BAD-ELF app. You would click on the elevation orthometric height option. And you're given two options. What do I want to see when I'm in satellite-based mode, which would be SBAS or autonomous, and what do I want to see when I'm getting a corrected solution? So in this case, it's going to drive to one of two screens, which will allow you to select the geoid that you prefer in each one of these models. These settings will propagate into the BAD-L Flex and be stored with the BAD-L Flex app. So in the future, when you're looking at your height measurements, you're going to see all this information available. So what does that look like on the app? Well, if we look at the screen capture on the left, you're going to see, based upon what the GPS receiver is telling the app, I'm operating and using this particular geoid. You'll see your ellipsoidal heights, you'll see your geoid heights, the pole heights and offsets that are measured by the antenna, and your final orthometric heights. The screen on the right is the same kind of screen that you would see on a BAD-L Flex. And if you'll notice that we're showing the model in use. So the model in use on the left, having been in SBAS mode, I switched over to RTK on the exact same point. And you could actually see that there are minor differences, which is what you would actually expect. So auto switching, this is kind of what it means. Had I switched and seen this on the, or done the RTK on the, before I did my screen capture on the left, you would have seen Geoid 18 as well. So these will always mimic each other based upon the mode the GPS receiver is operating in. So finally, let's go take a look at what we've added to the data logging. So when one is doing data logging on a BAD-L Flex, we store everything into a CSV file, and I wanted to really unpack what the CSV file looks like so you could understand exactly what's getting recorded, because we've added a number of fields to include this additional information. So one thing you could see is we're breaking out the elevation that is normally recorded from the GPS receiver. As I mentioned, that's an elevation based upon a world type geoid, which is this geoid here. We back that out and provide the ellipsoidal value, so you have that available as well. What I want to do is go into a little detail about this middle section. So as we're recording points and tracks and all the information that's capable of being recorded by the BAD-L Flex, we're saving the correction type. So you could see one point was recorded with SBAS, one point was recorded with RTCM or is in an RTK mode. We're showing you the correction distances and ages. So SBAS, not quite as relevant, but important. We're showing you the datum that's being used now. So all this data that's being recorded is now very self-descriptive. You can go back to each and every point and know, for example, that the second point I recorded was an RTK. I was connected to a particular mount point, so I could actually look back at what the coordinate system of that mount point might have been and know how I could interpret this particular data. Finally, as we move through, we've added this section on orthometric results. So the orthometric results, and these are all going to be on one line, just in case that question came up. We're going to show you the model of geoid that we used, the geoid that was calculated based upon that model at that time, given that the operating mode of the GPS receiver was either in an RTK or a standalone / SBAS mode. We're always going to record the antenna height, so whatever you program into the app as far as antenna height is, we're going to annotate that there. And the final orthometric height that's calculated. So one thing that I did want to bring up and note is this final orthometric height will include all the antenna offsets, whereas the ellipsoidal that you saw earlier does not. So if you wanted a real ellipsoidal value, you would have to subtract the 2.23 meters or whatever your antenna offset is. So I'm going to transfer this over to Nick because he's going to share with us how one would take this CSV data and bring it into a GIS. So Nick, would you like to get started with that?
Absolutely. Thank you, Larry. Let me pull up my screen. Hopefully, Larry, can you see a ArcGIS Pro desktop up?
I do. Perfect.
Okay, great. So let's go ahead and I'm going to bring up that CSV file that Larry was just mentioning, and I have a few of those columns that he was talking about highlighted. I wanted to show the data from the Flex natively before we got into the GIS. And most importantly for today, for what we're going to be looking at, I want you to realize there's a latitude and a longitude, so your X and Y or horizontal plane coordinates. All of the stuff Larry just talked about. But for today in GIS, I wanted to show you that there is the ellipsoidal height, remembering that ellipsoidal is basically a spheroid. It is a calculated perception of the Earth. It is not real world. That is what GPS or GNSS systems natively collect in without correction sources. And last but not least, at the end, this orthometric height column, which is the aggregation of everything Larry just discussed with offsets and geoids and whatnot. So when you're in ArcGIS, what you can do is you can do a add data. And so if I go to the add data, add XY data, I can use the geoprocessing tool to bring this CSV or Excel file directly into ArcGIS. So I would just simply navigate to the said file, which I have up and ready. And here is the file. Keep in mind when it's a Excel file, you actually need to click into the file because individual pages within the Excel sheet will be separated. I apologize, my computer seemingly is taking a little bit of time here. Usually this is very quick. There is the sheet. I click OK. Oh. And notice that ArcGIS is actually intelligent enough on its own to select the X field as longitude and the Y field as latitude. What we have to really think through here, though, is the Z field. And so the Z field, depending on whether you want the ellipsoidal height or the orthometric height, you have the ability to do either. So if you wanted to have your data brought into GIS with ellipsoidal height, what you would do is select the ellipsoidal M column. If you would like the data to come in as the orthometric height, you would select orthometric. Now, if you select ellipsoidal, recognize that you need to pick the correct coordinate system. So when you're talking ellipsoidal heights, we are actually talking about NAD83 2011 GCS. So what I would need to do here is actually select the correct one, which is NAD83 2011. And for the vertical coordinate, I'm going to do the same thing. Select NAD83 2011. Well, sorry, let me click none. ArcGIS is a little finicky. Okay, so if you are in ellipsoidal, NAD 1983 2011, and you would select that as your coordinate system, and you would click run, and you would get these points here. So I've already done it. So here is RTK ellipsoidal height. You can see the purple dot. If you were running this and you wanted to get orthometric heights, the difference would be is you would select, instead of ellipsoidal, you would go to the orthometric height. And for the coordinate system, now you would actually select a little bit different. So the X and Y maintains the same coordinate system based on the raw GPS data, but the Z system is going to change. We are no longer in ellipsoidal height, and so what we need to do is select NAVD 1988. So this NAVD 88 system is actually what orthometric height is best represented in. So then I would click OK, I would click run, and what you would see is now an RTK orthometric height point. Hey Nick, they're lining up. Exactly, because both of these data points that we brought into the GIS, horizontally speaking, are in the exact same coordinate system, NAD83 2011 GCS. But what we're talking about is height. And so what we need to do to really inspect what these data points look like is we need to go into the three-dimensional space. And so when Larry was talking about real heights, if you've ever brought in data and you've had data be below the surface of the Earth or floating in space, that's because your vertical coordinate systems are not aligning. Now, I know, and I should show you that because in two-dimensional space, I set the properties of my map, the coordinate system of my map, not the data point, not the feature class, but my map to a ellipsoidal height NAD 1983 2011. However, because I want it to be representative in real world, I set the arc scene, its properties up to the orthometric system that I was just mentioning when pulling in the points. NAD 83 2011 horizontally, vertically speaking, NAVD 1988. So check it out. If I get rid of the ground and I bring in the ellipsoidal height point, you see it is there. And if I bring in the orthometric height point, you'll see that it is actually above where the ellipsoidal point is. And so what you'll see is when I load up the ground in three-dimensional space, the RTK orthometric height is exactly lined up on the surface of the Earth, whereas the RTK ellipsoidal point is now floating beneath the surface of the Earth. So if you have ever had an issue aligning GPS data, or let's say LiDAR data or drone photogrammetry, this is usually what is happening. It's a difference in coordinate systems, vertical coordinate systems to be more specific, and then potentially between ellipsoidal height and orthometric height. So I just want to conclude, and I'll hand it back over to you, Larry, that by downloading the CSV right off of the Flex, it's very simple to add XY data. Simply select if you want to do it ellipsoidal or orthometric, bring the data in, and then set the scene or the map's coordinate system up appropriately to match your data point, so everything is driving on the same line, and you are off to the races. You have great data to tie down three-dimensional data sets like LiDAR, remote sensing, any type of remote sensing data set. So that is how you can get this pretty awesome data into a GIS. So I'm going to stop sharing, and Larry, I'm going to hand it back over to you if you'd like to share your screen, and I will mute myself.
All right. Well, I will share my screen, and lucky everybody who's on the call. one of you is going to get a hat. So we'll process that within the next day or two, and Nick or I will actually reach out and we will share with you one of these styling hats. But what's more important actually is likely what's next. Thank you for attending. We just want to let you know that this support will be available about mid next week this time. Reach out to Nick or I at sales@badelf.com. And of course, we'll always be happy to take questions. But we thank you for attending. We're really excited about this new feature, and just having the ability for this to operate standalone on the receiver or through the app is really going to provide a lot of value to folks who really need to have that extra bit of accuracy and information about GPS height. So I'm